Hi there, students. This is Mrs. Brunk. Welcome to class. In the last lesson, we started looking at sequences and series, and really was sort of an introduction to sequences and series, and we really looked at, kind of some all mixed together, but really more just looking at the notation and kind of some basic ideas about it. Today, we're going to dig in deeper and specifically focus on those sequences that are called arithmetic sequences, and sometimes I refer to them as linear sequences because they behave like a linear equation. And I think we looked at a few of those in the last lesson as well. So by definition, an arithmetic sequence is a sequence in which the difference between terms is constant. And you remember when we talk about lines, we say the difference between points on the line are constant. They're at a constant change or the slope. And so that's why we can kind of correlate the two and use some things that we know about that. So that common difference that we're going to see, this difference between two terms being constant in an arithmetic sequence, is actually called the common difference, and that's the numerical difference between two terms. In other words, how do they differ when you compare them by subtracting? So that really is similar to when we talk about slope with linear functions, and so it's almost kind of like the slope, or the m, in y equals mx plus b. So we're going to start off kind of slow, and we're going to just take a look at some arithmetic sequences, and we're going to see if we can figure out the common difference, and then just generate the next three terms in the sequence. So this first sequence, 5, 8, 11, 14, 17, well, clearly the difference between the terms is going up by 3. Oops. So I can very easily generate the next three terms just by continuing that pattern and adding 3. So the next term would be 20, the next term would be 23, and finally 26. Now that one was clearly arithmetic because you could see that constant change was adding 3 each time. Now, we don't want to just assume because the first couple in the sequence that are given have a common difference. That doesn't necessarily mean that the sequence is arithmetic. You have to, and really your best guess about what kind it is going to be based on the evidence they give you, so the terms they give you, and if you can see that common difference between all of those. So you really don't want to, skip that step of really checking to make sure that that continues throughout all of the terms that are given to you. So, looking at number 2, the first thing, we want to do is look to see if there's a common difference. So, and if so, then we can give what that common difference is and generate the next term. So, like on that first one, I would say the common difference is positive 3. So, on the next one, I can see the first two terms, well, it must be going down. So, it's going down by 7. Then from 16 to 9, it goes down by 7 again. From 9 to 2, down by 7 again, and from 2 to negative 5, going down by 7 again. So this one is arithmetic. The common difference is negative 7, so it's going down by 7. If this was like a line situation, the slope would be negative. And then to generate the next terms, I'm just going to continue subtracting 7. So subtracting 7 from negative 5 is negative 12. Then subtract 7, negative 19. And then subtract 7, negative 26. And continues on. So we're going to go ahead and designate these next 4 as the you try questions, and going to have you pause the video and give these a try. Remember, you're going to check to make sure it is arithmetic. If it's not, you're just going to say no and move on. If it is, we want to figure out what that common difference is, and we want to generate the next 3 terms in the sequence. So please pause the video now and complete 3 through 6 as you try questions. So thanks for giving those a try. Number 3 and 5 were not arithmetic, but 4 and 6 were, with the common difference on 4 being negative 2 and the common difference on number 6 being 12. So now that we understand exactly what an arithmetic sequence looks like, we're going to take a look at how we can write an arithmetic sequence. And really there's two distinct ways to two ways that really, are just, I guess they're not really distinct. They're basically the same thing, but kind of a little bit different approach to writing arithmetic sequence. And one of them is really tied right into slope-intercept form. And so, that's y equals mx plus b. But because we're not dealing with x and y, we're dealing with a sub n and n, we would say you could find this by taking a sub n, and that's found by taking the constant difference, which is like the slope, multiplying it by n, the term in the sequence, which is like the x value. And then usually the b is like the starting value. Well, in this case, sequences start at the first term. We call it the first term, the second term. But when you think about linear functions, that y-intercept is actually always the value when the input, or x, is 0. So it's almost like I'm finding this formula based on the 0 term, and so we would call that a sub 0. Now what that would mean is that we would have to use a term that's not listed in our sequence. The a sub 0 is not ever listed because we start the first term, so we would have to work backwards to find that. Now an alternative to that is, and how you'll see this done sometimes, is they'll use the first term, and so that would be that the nth term, a sub n, is going to be equal to the constant difference times n minus 1 plus a sub 1. Now I just personally think the first one is a little easier, and it's something I already know based on slope-intercept form, and so that just would require us to then take a moment right at the beginning when we first see a sequence and work our way backwards to figure out, in other words, take that common difference and work backwards to find out what the 0 term is instead. So again, you can think about it two different ways. If we use this formula right, the second formula here, then we would use a sub 1, and which would be the first term, and if instead we used the other formula, then we would be using a sub 0, and a sub 0 is, on the other hand, is the 0 term, or the term before the first term. But in both cases, the d is the constant difference, and that's, again, similar to the slope. So let's take a look at using these formulas to generate a rule, explicit rule for a sequence. So at number 7, I see the sequence starts at -5, -1, then 3, then 7. So I can see what's happening is here is it's adding 4 each time. And so that constant difference is positive 4. Well, if I want to use the little simpler formula, I'm going to think and work back and say what would be the 0 term. And if I worked backwards, I could see that that 0 term would be, instead of adding 4 to go forwards, we're going to subtract 4 to go backwards, so that would be -9. And so that's my a sub 0. And so now I could write my formula, explicit formula, a sub n is equal to the constant difference, which is 4 times n minus 9, or plus -9. Now alternatively, if we use the kind of the more common formula, you'll see we would have to say a sub n is equal to the constant difference, which is 4 times n minus 1, and then minus 5. And so using that formula going forward to find other terms would just be more difficult because it's just a little more complicated formula. So I'm really more of a fan of the one based on slope-intercept form, which just, again, requires you to just work backwards and find the 0 term. So let's take a look at number 8, and then we'll do a couple U-tries. So this one is 20 and then 11, so it's going down, and then 2, and then -7 and -16. So it's going down each time by 9. So the common difference is -9. The 0 term, again, if I worked backwards and I thought back, instead of subtracting 9 going forward, I would add 9, then the prior term would have had to have been 29. That's my a sub 0. And so my formula would be a sub n is equal to -9 times n plus 29. Now both of these questions ask me to then use this to find a certain term, so I need to go back and do that on number 7. So they want me to find a sub 24, which means plug 24 in, and if I plug 24 in, multiplied it by 4, and subtracted 9, that would be 4 times 24 minus 9. The 24th term would be 87. And then in this particular one, they wanted the 15th term, so that would be negative 9 times 15 plus 29. So that gives me a sub 15 being negative 106. So if you want to test yourself, you can do 9 and 10 as you try questions. You can pause the video and then test yourself to see if you understand this, tune back in. Otherwise, if you feel confident, you can go ahead and turn the page and we'll continue with the lesson. So pause now if you want to do the U-tries. So if you tried those U-tries, these are the answers. If you need to pause the video to check your work, feel free to do so. And then tune back in, and we're going to continue on with the next section of notes. So our next learning goal is to see if we can find an arithmetic rule, explicit rule, if we know terms that are maybe not sequential. So the directions say if the given terms are part of an arithmetic sequence, write a rule for the sequence and then find a sub 12. So you'll notice that I don't have a bunch of terms in a row where I can clearly see what that common difference is. So what I really actually have is the first, and then I have the third. Now these are not very far apart, so what I could do is actually just figure out how much it's changed and then see how many changes occurred in the meantime, like how many terms was the change applied to over that stretch. So I went from 3 down to negative 7, so that's going down 10. So that means since it must have changed twice in between there, that middle term could be generated just by subtracting 5, which is half of 10. So we could, since these are really close together, we could kind of just work through it mentally. But what about if, they're further apart, it's just a little less clear. So I really like to think about this, since we're kind of on that trend of linear equations, and think about these two terms as ordered pairs. So this first term, a sub 1 equals 3, would be like the ordered pair 1, 3. So like my ordered pairs, instead of being x's and y's, are like n's and a sub n's. And the next one would be 3 and negative 7. And then I could just simply calculate the d by using the slope formula. So I could see that the change in the actual terms are negative 7 minus 3, and that happens over a stretch from the first term to the third term, so 3 minus 1, that would be negative 10 divided by 2, which is negative 5. So between terms, the change is negative 5, the d is negative 5. So now since I actually do have the first term, I could easily work backwards to find the 0 term. I know that instead of subtracting 5, I'd have to add 5 to go backwards. So this 0 term, a sub 0, must be 8. And so to write my formula, it would just be a sub n is the constant difference, which is negative 5, times n, and then plus the 0 term, which is 8. Now I can easily figure out what a sub 12 is. Just plug 12 in and find my value. So if I plug 12 into the function, I would get negative 52, because that would be 12 times negative 5, which is negative 60, plus 8, that's negative 52. So let's try one more. So using an ordered pair notation to represent this, that would be the first term, n is negative 17. The 24th term is 6. So finding the difference in the y terms, or the difference in the actual terms of the sequence, 6 minus negative 17, and then the difference in the actual term numbers from the 24th to the 1st. So that's actually 23 over 23. So actually the common difference is just 1. each of these terms is just increasing by 1 every time. So when I go to write my formula, a sub n, the constant difference is 1. I mean, it's not really necessary to write the 1 in front of the n, but just to kind of really emphasize that that's the d. And then if I worked backwards from the first term, so it's like negative 17, and then dot, 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 all the way down here to the 24th term is 6, but working back from the first term to get the 0 term would just give me negative 18. So instead of subtracting 1, I'd add 1. So this would be 1n, or just n, minus 18. And now I could use that to find a sub 12. And a sub 12 would be 1 times 12, which is 12, minus 18, and that would be negative 6. Now I don't have an example like this here in the notes, but let's say you came across one where you were not really close to the 0 term, and so it would be really difficult. You'd have to kind of work backwards quite a bit to find the 0 term. Instead, what you could do is, so let's say you had, say for instance, so you had a sub 10 equals 14, and say a sub 15 is negative 1. So again, I could use my whole ordered pair thing to say, you know, this is 10, 14, and this is 15, negative 1. Sorry, my stylus is not working very well today. And then, so then I could calculate my slope by just doing the difference in the y. So that would be, see, negative 1 minus 14, and then 15 minus 10. So let's see, that would be negative 15 divided by 5. Oops, that doesn't look like a negative 15. 15 divided by 5, which is negative 3. So that common difference would be negative 3. But then in order to find the 0 term, you'd have to work backwards all the way back from 10 to the 0 term. So instead what you could do is you could use that general formula and say a sub n equals d times n plus a sub 0. And you could actually find, just like we find y-intercepts when we do linear equations, by just picking one of these ordered pairs. So let's say I pick this one right here, and I could plug in the term, which is 14, and for a sub n, I could plug in that common difference I just found. I know that that's the 10th term, so I'm just plugging in like sort of like my x and y, like I do to find y-intercept, and now I could just solve the equation here to find out what the 0 term is. So negative 3 times 10 is negative 30, and then in order to find the 0 term, I just would have to add 30 to both sides, and that would make 44. So that means that initial term must have been, or in other words, a sub 0 was 44. Then I could use this and my constant difference to write my equation for that sequence. So again, if it's a little harder to figure out that 0 term is, you can always go back to what we know about finding a y-intercept. Just take one of the terms, one of those ordered pairs, and your common difference that you just found, and plug them back in to find a sub 0. So in our final learning goal, we're going to look at arithmetic series. And remember that a series is the sum of a sequence of numbers. Oops. Now, when finding the sum of an arithmetic series, we can use the following formula: s sub n equals n times a sub 1 plus a sub n divided by 2. So real quick, if we think about how we did this in the first lesson, and what we would do to find a series is we'd have to generate all the terms. Let's say they wanted us to find the s sub 10, we'd find all the first 10 terms, and we'd just simply add them up, just like the long way. So with this formula, what it's basically saying is, if you want to find the sum of the first 10 terms, you don't actually have to find all 10 of those terms. You really just need to know the first term and the 10th term, and then what you're going to do is actually average them. So this part right here is actually saying this is the average of, it's the average of the first and the nth term, because we're adding them together and dividing by 2, which is averaging them. So essentially what we're doing is we're finding an average of the first and the last term that's in this sequence that we want to find the sum of, and we're averaging them, and then we're multiplying by n, which means how many terms there actually are in this series we're trying to find. So that actually makes sense if you think about what each of those things represents. So again, n is the number of terms that we want to actually find the sum of. And then a sub 1 is the first term, and a sub n is the nth term. So we're going to go ahead and test out that formula and see if we can find the arithmetic series or sum that's indicated. So looking at this first example, in number 13, it says that they want me to find s sub 10. So s sub 10 is the first 10 terms. Now I don't have the first 10 terms here listed. It wouldn't be very hard to actually generate them. So I could just continue on with this pattern and then until I got to the 10th term. But we've been talking about writing equations, so I'm going to write the equation for this and then just plug in 10. So I know that a sub n here would be found by a common difference of 2. These are going up by 2 times n. And if I worked backwards to find the 0 term, it would actually be 0. So this formula is a sub n is equal to 2n. So I could find a sub 1. So a sub 1 would be 2 times 1, which is 2. I could find the 10th term because I'm trying to find the sum of the first 10 terms. So a sub 10 would be 2 times 10, which is 20. And then this is how I could plug them in the formula. It would be, I'm going to find the sum of 10 terms, so n is 10, times the first term, which is 2, plus the 10th term, which is 20, divided by 2. So the average of the first and the 10th, 2 plus 20 is 22, divided by 2 is 11, so this would be 10 times 11, which is 110. So instead of having to generate those all up and add them at the end, I just was able to find the first and the 10th and use this formula. Let's take a look at number 15 because that notation is a little bit different. But remember, that just means that we want to find the sum of the terms from the 1st to the 12th. And that way, this one is kind of nice because like if, let's say, you wanted to find the sum of the, the 4th through the 16th or whatever, you could just change your x sub 1 to be 4 and your number on the index on the top to be whatever the last term you want to add. And we could still use this formula, but they wanted the 1st through the 12th. And so if I plugged in and found, so they already have the formula, so I could find a sub 1 just by using that formula, plugging in 1. That's 6 times 1 minus 4, which is 2. And then a sub 12, which would be that last term in the series, would be 6 times 12 minus 4. So that's 72 minus 4 is 68. Now I'm going to use the formula, and I can find that sum just by taking, I'm finding 12 terms, the product of 12 terms, times the average of the first term and the 12th term. So 2 plus 68 is 70, divided by 2 is 35. So that's 35 multiplied by 12, which is 420. So the sum of the first 12 terms, instead of having to generate all those 12 terms and add them up, I just use this formula to find out it would be 420. So looking at number 16, so that's a little bit different because this time it's starting with the 8th term and going to the 17th term. Now that is 10 terms because, we've got 8th and the 9th, the 10th, and so on. There's actually 10 terms there in between the 8th and the 17th. So it's kind of like I'm finding a sum of 10 terms, or s sub 10. But we're starting with the 8th term, so I could plug 8 into the formula. So I could find instead a sub 8, which is negative 2 times 8 plus 3, which is negative 13. And then I could find the a sub 17, which is negative 2 times 17 plus 3, and that's negative 34 plus 3, which is negative 31. And then I can, since I know that there's 10 terms that I'm looking for when I use this formula, I'll say that's 10 times the sum of these two. So I'm going to add, oops, that's supposed to be a 13, not a 12. Negative 13 and negative 31 divided by 2. So the average of negative 13 and negative 31 is negative 22, and negative 22 times 10 is negative 220. So my answer, my sum, is going to be negative 220. So again, it works for whether you start at the 1st and end at the 12th, start at the 8th, end at the 17th. It's really just flexible. You just have to then consider whatever the first term you're starting with will be kind of like your a sub 1, and your final one will be like your a sub n. And you can use this in, any instance where you have an arithmetic sequence that you're trying to find the sum of a certain number of terms. So that does it for today's lesson. Thanks for coming to class.